Okay, let's get started. What we want to do today is phase diagrams and how we use phase diagrams to design processes, gain insight into how materials behave, and so on. Recall our free energy of a multi-component system that can form a solid solution is really controlled by three terms: the energy of the solution at absolute zero, the specific heat, and finally the configurational entropy, which is specific to a solution and arises from the fact that there are many, many different ways to arrange the atoms in a solution, each one of which contributes to the entropy. Remember, as a consequence, the configurational entropy for a random solution can be written in this way, which gives you at least a vague understanding of what it should be like in all cases. The configurational entropy is related to the logarithm of the number of distinct ways of arranging the atoms on the sites of a solution. If they're Na atoms of type A and Nb atoms of type B, then the total number of ways that they can be configured, whether n factorial ways of arranging n atoms over n sites, n a factorial of those are redundant because they just interchange identical A atoms, n b factorial of those are redundant because they exchange identical B atoms. So this is the total number of distinguishable ways of arranging those atoms. Now if we use Stirling's approximation in mathematics and just plug in, we get the configurational entropy of a random solution is minus nk x log x plus 1 minus x log 1 minus x, where x is simply the mole fraction of the atom fraction of the A component. Now this is an indication of how the configurational entropy works. This is correct in the limit that x is either very close to 0 or very near to 1, because a dilute solution, it's sufficiently dilute, will always behave like a random solution. When we get to significant values of the fraction, however, this number becomes a bit off because there will be tendencies of atoms to either like or dislike like atoms, so the arrangement of atoms will not be completely random. They will tend to cluster or not cluster depending on whether they like each other, and that has an effect. But this is at least an indication of what the configurational entropy will look like at all compositions. One of the most important consequences of that is that solubility is universal. And you can see that by simply using the fact that suppose we take two pure components, bring them into contact with one another and say, are they going to mix? Will there be any solubility? Well, since the first mixing will be a dilute solution, I can use the random solution expression for the configurational entropy. So I get the free energy is just some function of concentration plus this term. If I differentiate that with respect to x to see whether the free energy goes up or down as I increase x, then in the limit x equals 0, this second term goes to minus infinity for t anything other than 0. So as a consequence, the first little bit of solute I add gives me an infinite negative slope in the free energy. There's no way to stop that from happening. So that tells me two things. Everything is at least a little bit soluble in everything else. And the limit of the change in free energy with respect to concentration and temperature, the limit as x goes to 0 is negative infinity. For equilibrium phase diagrams, I'll come back to use that in just a moment. A phase diagram is simply a map that shows the equilibrium phases, the state of aggregation, crystal structure, solid, liquid, vapor, that the material will want to take on as a function of, well, if it's a binary solution, and if we're at ambient pressure, which is the case we'll examine, as a function of the temperature and the concentration. We're going to focus today, we already talked about phase diagrams of one-component systems. They're pretty simple. So today we'll talk about the phase diagrams of two-component systems, which I introduced last time. A little bit more complicated. What I want you to learn is how to read any binary phase diagram, how to determine what phases are present at given values of temperature and concentration, what their concentrations are, and then how to understand and use, in fact, two phase diagrams: the phase diagram of an ideal solution and the phase diagram that we call the eutectic phase diagram, which you studied in the laboratory. To construct phase diagrams and understand what they are as they are, the first thing we need to understand is how the free energy of a solution changes as we add solute into a pure component. If we have here the free energy of a pure component, and we say what happens to the free energy as a function of x as we start adding solute, well, we already know because we just proved that this curve for free energy as a function of x will start out vertically down, because the first little increment of solute gives me an infinite negative slope in the free energy. So if I construct a curve of the free energy of a function of x, it starts out vertically down. I can easily show, and I will in just a second inferentially, that that curve must be concave up like this. Otherwise, the solution will be unstable. So the free energy curve for a stable phase, a stable solution at given temperature is fixed here, is a curve that looks like this. It's concave up. What happens if more than one phase can exist? We did this last time. I'll do it again because it is the important thing to know here. Suppose we have a system which at a given temperature has two possible phases, or two phases of interest, alpha and beta, and those two phases have free energy curves that look like this, both asymptoting to the axis vertically up, both concave up. Either one of these could be a stable phase. So we ask ourselves, what does the system want to do thermodynamically? Does it want to be in phase alpha? Does it want to be in phase beta? Or does it want to be in some mixture of the two? And if it wants to be in a mixture of the two, what are going to be the compositions and fractions of those two phases? Well, we can easily find that if we happen to know these free energy curves. We find it in the following way. Suppose that we consider a composition, let's say x here. Now let's imagine that the system is in phase alpha. If it were, its free energy will be here. We want the lower free energy, so it obviously isn't in phase beta. It doesn't want to be. But could it be in two different phases? If it were in a mixture of two phases, alpha and beta, then let's take a possible composition for the alpha phase and a possible composition for the beta phase and find out what the free energy of the aggregate would be. If we adjust the amounts of alpha and beta, I won't do the math, I'll just tell you the answer. If we adjust the amounts of alpha and beta so that the total concentration is right here, then the free energy will be, if I take a straight line that connects the hypothetical concentration of alpha to the hypothetical concentration of beta, then the free energy of the mixture will be right here, where that straight line cuts through the vertical dotted line at the composition x. That simple graphical construction, which you can prove mathematically, it's proven in the notes, will give you the free energy of any possible combination of alpha and beta. When I just look at this, it should be kind of obvious that whatever combination of alpha and beta I use, unless I have 100% alpha at composition x, any line connecting the alpha and beta curves is going to intersect this dotted line at a point above the free energy of the alpha phase at composition x. Therefore, if I want to minimize the free energy in this situation, this composition, I want a 100% alpha solution with composition x. Well, now suppose I have a different composition. Suppose I'm out here now, as shown in the lower figure, this new composition x. Now, the alpha phase would have this free energy where this vertical dotted line crosses the alpha curve. Obviously, the beta phase would be higher, so if we're going to be one phase, will be alpha, not beta. However, now look at the possibility of having a mixture of alpha and beta. Once again, graphically, if I just connect a potential alpha composition to a potential beta composition, then the free energy of the mixture of the two phases would be where the line that connects those compositions crosses the vertical dotted line at composition x. For most compositions, that would be above the free energy of the alpha phase. So most mixtures would be unfavorable. However, if you look at mixtures of alpha with a composition X alpha and beta with a composition X beta, you suddenly get a situation in which forming a mixture makes the free energy go down. Not only does it make the free energy go down, the free energy becomes minimum, reaches a minimum value when the alpha and beta compositions are determined by what we call a common tangent line, a straight line that is tangent to both the alpha and the beta phases. That minimizes the free energy. It does some other things as well, because the tangent, I guess that's on the previous slide, if I just take the tangent line to the free energy curve, the derivative of G with respect to X at that point, that is the free energy, that is the chemical potential of the solution at composition X. So if I come back to the common tangent line, if these two phases, alpha and beta, have the same tangent line, they have the same chemical potential. Now, when we found the condition of chemical equilibrium inside a solution, inside a phase in general, it was that the chemical potential had to be the same everywhere. So this tells me that if I look at these curves, if I can find a common tangent line between them, then the two phases, the two compositions, the phases alpha and beta at the compositions given by the common tangent line, not only provide a minimum value of the free energy when X is anywhere between X alpha and X beta, but they also give me a situation in which these two phases are in chemical equilibrium with one another. So this is the equilibrium situation here. So what do I have? Do it the next slide or do it here? Well, let's do it here. If I ask myself at the temperature at which I've drawn these curves, what is the preferred phase going to be as I increase the composition from pure A to pure B? The answer is simple. I construct a common tangent line between the alpha and beta curves, as shown here in the bottom. If my concentration is less than X alpha at one end of the common tangent, then my preferred phase is pure alpha, 100% alpha. If my composition is greater than X beta, my preferred phase is 100% beta. If, on the other hand, my composition is between X alpha and X beta, then my preferred phase is a mixture of the alpha and beta phases, where alpha has composition X alpha and beta has composition X beta. In a moment, I'll show you the lever rule, which tells you how much of each we have in the solution. Obviously, with the amount of X alpha phase and beta phase must be such that the overall composition is X. So as I move across this line from X alpha to X beta, I start out at 100% X alpha, I begin to introduce beta phase, more and more and more beta phase until I get to X beta where I'm 100% beta phase, and then I stay there for higher concentrations. So if I know the free energy curves and use the common tangent rule, then I can easily see how the phases are going to be related. Yeah?
So the solution will split into two phases?
Yes.
And the composition will be X alpha and X beta?
Right. As I increase the composition in this region, what changes are the volume fractions of the phases. Their compositions do not change. Their compositions are fixed. Okay? We'll see that in a slightly different way in just a minute. We can have more complicated situations. Suppose there are three phases, alpha, beta, and gamma. In the upper diagram, which would refer to one particular temperature, the lowest common tangent line connects the alpha and beta curves but does not touch the gamma curve. Therefore, the gamma phase would not appear at equilibrium. And my situation would be alpha phase between A and X alpha, increasing fraction of beta phase between X alpha and X beta, beta phase above X beta. But now let's suppose that the gamma phase is cut by the common tangent line. Its free energy comes down a bit. Now I have three phases as I come across. Alpha phase below X1 in this diagram, alpha and gamma with an increasing fraction of gamma as I increase from X1 to X2, all gamma phase between X2 and X3, beta phase appears at X3 and increases in volume fraction to X4, and then I'm 100% beta phase. So that is is what would happen. That's how I could calculate the phase diagram, find the equilibrium phases at every temperature and composition if I knew these curves. Well, of course, in general, I don't know the curves, but what I do know is that curves exist, and therefore I can kind of see the way phase diagrams should look. I'm likely to have a solid solution near both terminus, A and B. In between, I may well have two-phase regions. And within the two-phase region, as I move the composition through the two-phase region, I will change the phase fractions, but will not change the compositions of the two phases. They're fixed by the temperature. Yeah? One temperature, right. If I change the temperature and let this happen, then I generate a full TX phase diagram. And here are a couple of diagrams that I might generate, and I'll show you how in just a minute. The equilibrium phase diagrams, TX, the way we normally plot them, we can, of course, have pressure as a variable, too, and we would if for some reason the pressure were enormous, but for most material processing, we're around ambient pressure, so we don't generally worry about that. These are the diagrams you would usually see plotted out. These phase diagrams are maps. They are maps of the phase relations I was just showing you. Take the one on the left, which is a map for A and B. This should be alpha instead of A dot, I'm sorry. A and B that form solid solutions at all low temperatures and liquid solutions at all high temperatures. Well, what is this telling me? From this phase diagram, if I am in this phase field, I would be 100% alpha down here. If I'm up here, I would be 100% liquid. Now, with these intermediate temperatures, however, I break up into two phases in intermediate compositions. So what that's telling me, if I take a temperature between TA and TB and start over here, I'm 100% liquid until I reach this line. Between this line and the other line on the side of this two-phase region, I can take two phases, a liquid and an alpha phase, where the liquid has the composition on the left-hand side, the alpha has the composition on the right-hand side. When I exit that two-phase region, I'm pure alpha all the way to TB. The eutectic diagram is a bit more complicated, but you can read it in pretty much the same way. And what I'll do now is turn how you read a binary phase diagram. A binary phase diagram contains, you can read three types of information from a binary phase diagram. For any given temperature and composition, you can find out what phases are present, what the compositions of those phases are, and what the fractions of those phases are. Okay, so let's do that. What phases are present? Suppose our T and X of interest is right here, the black dot in the figure. Well, that's in a two-phase field. So if I'm at that temperature and composition, I have two phases, alpha and beta. What are the compositions of the two phases? Well, just from the construction that generated this phase diagram, if I draw a horizontal line straight through that dot, on the left-hand side it hits the alpha phase field, on the right-hand side it hits the beta phase field. Where it hits the alpha phase field gives me the composition of the alpha phase. Where it hits the beta phase field gives me the composition of the beta phase. So if I'm right where that dot, if that's my T and X, I have a two-phase mixture of alpha that has this composition and beta that has that composition. How much of each do I have? Well, I can find out how much of each I can have by simply saying that the fractions of alpha and beta must be such that my overall composition is equal to X. I won't go through the math, it's in the notes, but what you can show very easily, in order for the overall composition to be X, for mass to be conserved, the fraction of the alpha phase must be X beta minus X divided by X beta minus X alpha. Similarly, the fraction of the beta phase is X minus X alpha, this, divided by X beta minus X alpha. This is called the lever rule because it says that the fraction of alpha phase is the lever on the other side of the phase point. This length here divided by the total length of the line, and similarly for the beta phase. So give me any point, any combination of temperature and composition, I can immediately read from the phase diagram what phases are present, what their compositions are, and what their fractions are. Of course, if this falls inside a one-phase field, I'm 100% alpha, and the composition is just the overall composition of the solution. Here I'm 100% beta. Incidentally, note one other thing. On the boundaries here, we always have alpha and beta solid solutions, which are mixtures of A and B. I know you're always going to have that, because I know that B is always at least a little bit soluble in A, therefore alpha, and A is at least a little bit soluble in B, therefore a beta solid solution. These two curves will asymptote to 0 and 1 as temperature goes to 0, but they won't reach 0 and 1 until temperature reaches 0 by the second law. Okay? So those are the three things I can read about any phase diagram. I've shown you simple phase diagrams. A lot of phase diagrams aren't very simple at all. This is the aluminum copper diagram. In fact, up here, there's still some dispute about what's up there. And in fact, I was at a conference in San Diego last week, and people got a bitter fight about what's in this region up here. It turns out to be actually very relevant to what happens if you, in certain reactions that happen in solders, because you will have aluminum as it can be a useful solute to add to tin copper solders, which are of interest as lead-free solders. And so what's happening up here, the copper-rich side of this aluminum copper diagram, turns out to be of significant interest in what the aluminum will do when you put it into a tin copper solder. So all these little regions up here, which are very hard to get hold of, are a matter of some dispute at the moment. But think something like this. Okay, I've got the theta phase, here I've got the eta 2 phase. Never mind what they are. They're complicated crystal structures, believe me. This is aluminum 2 copper, actually, which is it's sort of like aluminum 2 copper, which is the hardening precipitate in aerospace aluminum. Anyway, suppose my point is right here. What have I got? I've got a mixture of theta and eta 2, whatever those phases are. What are the compositions? Here's the composition of the eta phase. Here's the composition of the eta 2 phase. Weight percent there, how many percent of time? What are the fractions? I get the fractions from the lever rule. Remember that the lever in the lever rule runs just across this 2 phase region. So the lever is from here to here. So what happens is I increase the weight percent copper and I get up here to this theta region and I keep going. I have pure theta. Push the composition up a little bit, I start seeing some of this eta 2. As the composition goes up, I see more and more of the eta 2 until finally I'm 100% eta 2. And then on the other side of that field, this zeta 2 starts coming out. And you don't want to know what the structure of that is, believe me, unless you happen to be in the aluminum copper solder business. Finally, over here we have a pure copper phase. But no matter how complicated the phase diagram is, reading it is straightforward. Your T and X give you a point. In a binary phase diagram, the point is either in a one-phase region or a two-phase region. If it's a one-phase region, the phase and composition are obvious. If it's in a two-phase region, you determine the phases from the phase field, what phase is bound to this phase field, the compositions by drawing a straight line across the phase field and seeing where it intersects, and the fractions from the lever rule. And that's how you read any phase diagram, no matter how messy it may be. Yeah?
Were you saying earlier that you have phase separation because the second derivative of G with respect to X is positive? You have separated.
Oh, right. I said I'd tell you why it has to be concave up. Let me go back to that. You see this common tangent construction? Okay. These curves are both concave up. So, for example, suppose I ask the question of would alpha want to divide into two regions of different composition, both with the alpha phase? Well, obviously not, because that free energy would be up here. Now let me turn it around and have this thing be concave down. If it was concave down, then this point would be down here somewhere. And you would want to spontaneously divide into two regions, both with the alpha phase, but with different composition. Therefore, the solution would be unstable. Well, you might ask, does that ever occur? Yes, it does occur. There's a whole set of reactions. I'll briefly touch on them. The theory is a bit beyond this course, but there's a kind of chemical decomposition in solids called spinodal decomposition. And what happens in spinodal decomposition is you get into a regime where this curve turns over, so it's concave down. And if you can get your system into that regime, the alpha phase will want to spontaneously divide into two regions, both of which are alpha phase, but they have different compositions. And the way that happens is kind of interesting. If you go into such a region, what will happen is you'll develop something like a sine wave, high composition, low composition, and the amplitude of the sine wave will just keep increasing until you get to an equilibrium state. So anyway, from the lever rule, it's obvious these curves have to be concave up if they're going to be stable. Okay, that's how you read phase diagrams. Now let's talk about why these two phase diagrams that I'm going to ask you to kind of understand look the way they do. Let's start out with solid solution. First of all, I'm lying to you. We use solid solution diagrams all over the place. We use them all the time. They are always inaccurate. The reason is that this doesn't obey the third law of thermodynamics. Go to zero temperature, it's still a solid solution. Every solid solution that's out there, if you go to low enough temperature and if you give it a chance, it's got to either order or separate into two components. It's got to do something to get rid of the solution and satisfy the third law. We use a lot of solid solutions all over the place in engineering. Usually we don't worry about that because by the time you get to a low enough temperature for those reactions to happen, you're at such a low temperature that atoms can't move very well anyway, so nothing does happen. But there are situations in which that fact comes up to bite you, and I'll mention maybe a couple later on in the course. But let's talk about the solid solution. This might be silicon germanium, for example. They form solid solutions at all temperatures, except for very low temperature where they work. Now, what kind of relation between the alpha and liquid curves is going to generate this kind of diagram? Well, suppose we're above the melting point of the B phase. The liquid must be stable everywhere. Both the liquid and the alpha curves must be concave up, so they look like this, with the liquid below the alpha at every temperature. Suppose we lower the temperature now, make it very low, we're down here somewhere. Then the situation must look like this. Both curves are concave up, and now the alpha curve